Hey everyone, and welcome. Today, we're diving deep into one of the absolute trickiest architectural challenges in data systems. How do we efficiently query complex, highly interconnected data? In modern engineering, we are rarely just dealing with isolated, perfectly flat data structures anymore. Whether you're building the backend for a massive social network, architecting a real-time recommendation engine, or trying to map out a complex supply chain or fraud detection network, your data is increasingly looking like a sprawling, continuous web. It's a huge shift from those predictable grids we used to rely on. So in this explainer, we're going to unpack the advanced concepts of graph querying. We'll look at the pretty severe limitations of traditional tools for this job, and then we'll explore some purpose-built models, specifically triple stores and SPARQL, that offer a dramatically better path forward. Let's get into it.
So let's just address the core tension right out of the gate with a question that almost every systems architect wrestles with eventually. Can you actually query highly interconnected graph data using a traditional SQL database? It's such a common dilemma. We all have these robust, battle-tested relational databases, right? They're the backbone of the industry. But when our data models shift from predictable transactions to highly connected, complex relationships, we really start to hit a severe impedance mismatch. Basically, does that familiar rows and columns paradigm still hold up? Or are we literally engineering ourselves into a corner by forcing a tabular model to do a graph's job?
All right, let's set the stage. Section 1, the graph querying hook.
To really evaluate our tooling, we first need to understand the data itself. Imagine a practical scenario with two people, Lucy and Alan. Notice that we're not just connecting simple, identical user records here. We've got a whole mix of entities, people, cities, states, countries, and even continents, all hanging out together in one continuous, interconnected graph structure. Instead of locking these entities away in rigid, separate tables with strict foreign keys, the data model relies on nodes and edges. For instance, we can map Lucy directly to Idaho using a born-in relationship, and then map her over to London with a lives-in relationship. Alan also has that lives-in connection to London, but a totally distinct born-in connection to St. Lo, France. And here's the crucial part. The locations have their own deep hierarchical edges. Idaho connects up to the United States, which connects to North America. London links to England, then the UK, and ultimately Europe. It's this fluid, flexible web where the relationships are just as important as the data points themselves.
The real headache starts when we need to pull broad insights out of these deep, cascading relationships. For this explainer, our goal is a classic graph problem. We want to find the names of everyone who emigrated from the United States to Europe. To do this, our query has to find people who have a born-in edge leading to any location that eventually rolls up to the US and who also have a lives-in edge pointing to any location that rolls up to Europe. The tricky part isn't the conditions themselves, it's the arbitrary depth. We have no idea in advance how many within relationships the database engine is going to have to follow to actually reach the target continent.
Let's see how our traditional tools handle this. Section 2, graph queries in SQL. So what happens when we try to run this highly variable query in a standard relational database? Well, SQL usually wants you to define your joins explicitly before it runs anything. But because our location hierarchy has a completely variable number of steps, someone might live in a city, inside a region, inside a state, inside a country, or maybe just directly in a country, the exact number of joins is just unknown. To get around this, SQL has to use something called Recursive Common Table Expressions, or CTEs, using the with recursive syntax. And mechanically, this is exactly where the pain begins. Under the hood, a recursive CTE forces the database engine to build temporary intermediate tables in its memory for every single hop in the hierarchy. It runs an anchor, stores it, runs a recursive member against that workspace, appends rows, and repeats until it's done. When you try to scale this across millions of nodes, all that constant temporary table building absolutely churns your RAM and tanks your performance.
And it's not just a performance issue. The cognitive load on the engineering team is massive. Get this, it takes 31 lines of incredibly complex SQL code just to execute this one emigration query. 31 lines. The code is heavily imperative, meaning you are practically micromanaging the database's execution plan. You have to manually define virtual tables just to find all the US location IDs, then make another set to traverse the European locations, then figure out the intersection of people born in the first set and living in the second, and then join the whole shebang together. That is 31 lines of fragile, totally unreadable code just to navigate a few logical hops on a map. It's practically the definition of developer friction, and it makes maintaining relational graph queries super risky.
So there has to be a better way, right? Section 3, Understanding Triple Stores.
Fortunately, we are not locked into the relational model forever. To get rid of that recursive join nightmare, we can look at data models that were literally built from the ground up to handle interconnectedness natively. Enter the triple store. A triple store is a totally different architecture where absolutely all information is broken down into simple atomic three-part statements: a subject, a predicate, and an object. Unlike relational databases that force a strict schema when you write data into tables, triple stores are incredibly flexible. Because everything is just stored as an independent triple, you don't need brittle table structures at all. The schema can just naturally evolve. If your app suddenly needs new entities or totally new types of relationships, you just write new triples. No database migrations required.
Let's quickly break down the mechanics because it maps perfectly to our graph. The subject is basically a vertex in our graph, like the entity Lucy. The predicate is the directed edge or the relationship verb. And the object is the target, which could be a simple string or integer or another vertex entirely. If it helps to think in relational terms, imagine every single triple is like a highly abstracted universal foreign key. The statement, Lucy, born in Idaho, captures that entire connection in one clean unit. Lucy is the subject, born in is the predicate, and Idaho is the object. Simple, right?
Just as a quick aside for some context, this architecture actually has deep roots in an early 2000s project called the Semantic Web, which was this big initiative to publish internet data in a universally machine-readable format. The data model they standardized for this was the Resource Description Framework, or RDF. Now, while the whole semantic web vision didn't quite pan out the way they expected, the RDF model itself turned out to be incredibly resilient for graph storage. Today, developers use specialized syntax formats like Turtle to write these triples. Turtle is super popular in graph engineering because it's so much more compact and readable than clunky formats like raw XML, letting engineers literally see the graph structure right in the code.
Okay, let's talk about extracting that data. Section 4, Querying with SPARQL.
Once you move to an RDF-based triple store, you obviously need a new way to query it. That's where SPARQL comes in. SPARQL stands for the SPARQL Protocol and RDF query language, and it completely flips the script on how we ask a database for answers. Instead of SQL's imperative style, where you're writing those messy recursive loops to tell the database exactly how to build tables, SPARQL uses declarative pattern matching. You just describe the shape of the data you're looking for using variables, and the query engine natively figures out the best way to traverse the graph to find it.
Think about the difference conceptually. With SQL, you have a tangled mess of recursive joins, forcing the system to generate all those heavy virtual tables. But with SPARQL, it's elegant. In SPARQL, variables just have a question mark in front of them. The engine lets you string relationships together using something called a property path. You just say, hey, find a person, follow their .bornin predicate, put a / to continue the sequence, and then use the .within predicate followed by an asterisk. That asterisk is the magic property path modifier. It tells the engine to follow that within relationship 0 or more times until it finally hits your target .location variable. No manual recursion. You are literally just drawing the path you want the engine to follow.
And the payoff for this is absolutely massive. Remember that nightmare US to Europe query that took 31 lines of brittle code in SQL? In SPARQL, it takes exactly 4 lines. 4. You just declare the pattern, find a person, trace their born-in path through any number of within edges to the United States, and trace their lives-in path through any number of within edges to Europe. Bam! Done. This is a game changer for maintaining a code base. You drastically cut down technical debt, you completely eliminate the headache of manual query optimization, and you're relying on an engine that is actually designed to follow these edges natively without blowing up your memory.
Let's wrap this up. Section 5, Summary and Final Thought. Let's synthesize what we've covered today. Relational SQL relies on tables and rows, a rigid schema. When you force it to walk down variable length paths, it has to use memory-heavy with recursive operations, blowing up your code to 31 lines of micromanagement. On the flip side, triple stores use that simple atomic subject-predicate-object structure, which gives you incredible schema agility. Path traversal is handled elegantly through declarative pattern matching with SPARQL, shrinking your logic down to just 4 highly readable lines. For a dev team, this isn't just about typing less, it's about fundamentally reducing the places where bugs can hide. It makes onboarding so much faster because the code actually reads like human intent, and it ensures your architecture won't just buckle under memory demands as your data gets more connected. So, I'm going to leave you with this to think about regarding your own data systems. Take a hard look at the code your team is running today. Are you constantly fighting against the grain of your data model? Are your engineers writing dozens of lines of fragile, recursive code just because you are forcing a relational architecture to do a graph's job? Realizing when a traditional structure is holding your interconnected data back is a true hallmark of strong systems design. Making the jump to a purpose-built model, like a triple store, might just be the exact architectural pivot you need. Thanks so much for joining me for this explainer, and keep questioning your architecture.